So the Poisson distribution, what's that all about? So that's the third out of the three ones we will meet today. Please get this feeling that these different distributions are coming out of different natural phenomena, right? They can be used for those situations that are like that. They cannot. It's not like a free pick from the shelves whenever you meet something. Oh, I think I like the Poisson today, so I do three tosses with my coin and I use the Poisson because that's a good one for me today. There is not a free pick. There are situations that are sort of matches up with the different ones. Now, the Poisson distribution is used, could be considered to be used when we count something, which is a bit that could be have any kind of number. There's no upper limit. Bacteria in a petri dish, for instance. Let us count them. Do I know in beforehand that I can only have between 0 and 20 successes? No, I don't. I count fish in Öresund. Do I know how many there would be when I take a sample? No. I count calls, I count events over time. So the Poisson distribution is designed for events, counting events in time or space, so to say. Often time, but it could be space, area, or volume. You could count number of gold pieces you find in a mine. Well, here's the short story. Here's the probability. Under certain assumptions about independence and no kind of clustering, it's kind of independent events all over, then the probability of getting exactly X successes is given by some parameter which is called the rate. That's the average number of events per time or per area, if it's kind of in a space-based situation. And it looks like this. And the nice thing about this, did I bring that? No, I didn't bring anything else. But the nice thing about this is that if you add all of those up, even as many as you couldn't do on your own, infinitely many. So this is the rate to the power of the number of possible events, the factorial, and then the exponential to minus the rate. What do you think this number adds up to? Remembering my definition of a density function, and now that you know that apparently this is a meaningful density function, what would this infinite sum add up to? 15? Of course. There's a bit of mathematical analysis in this. We'll not go there in this course to be on top of such infinite series like this. And yeah. And we could define the distribution function as the usual. It's the same formula as before, just aggregating those Poisson. Let's look at the example. I'm just going to check how much I brought there of different slides. Let's look at this one first. Here I have the largest fonts to tell the story. It's a little story. Let's assume, just for the case, that we have some event type. Could be hospital patients due to air pollution, just to pick out some odd thing that you might register. Maybe you found out, again we have this scenario that we assume that we know what's going on for this exercise of learning about the probabilities now. So let's assume that his history told us that on average we had 0.3 patients per day. How many days would we then on average wait for the next patient? Say I have a patient now. When would the next, How much is my expected time to wait for the next patient in such a random system with this intensity? 3, yes, 3.3 if we want to say it like that. Exactly, common sense rules. And we're going to get back next week to a distribution on those waiting times. That's called an exponential distribution, but that's a continuous one. But it lives within the same random process. This is actually also then called a Poisson process, if you want to see it with a time dynamical system like that. Anyway, now we're just counting the number of events. We could ask different questions. And again, the meaning by this slide is to make you remember that if you are given this story and this question, and then somehow you, in the first go, you wouldn't know this one. This is the story that might hit you as an engineer, right? Then you have to put it into formula. And I'd like you to be a bit careful about this in the beginning. You get some question, you get a situation described, put it into formula. Think about what the x is and what the distribution of that x is, and if you're on top of that, you're done, basically. You can do everything else from there. What's the probability that at most 2 patients on a given day, on a single day, are coming in? At most 2, that's 0, 1, or 2, right? At most 2. Usually I have myself to be really have to think carefully about those statements. Is it really one or the other? At most 2 to me, do you agree with me? That's 0, 1, or 2. Good. What's the random variable? Well, we count number of patients on a day. It could be anything from 0 to 1 million. Pretty unlikely with 1 million patients on a single day if we are talking about independent event modeling. We are not talking about nature disaster modeling, which is not independent events on the individual. We say that it's a binomial. We want to find the probability of x being less than or 2 with this intensity. We could start using the formula, right? And I warn you, or I encourage you, to think about the formulas, of course. Sorry for jumping. However, it's clear that we have this tool out here that makes our lives a little bit easier. The formula is not extremely difficult, as you saw, but now I'm going to add up 3 numbers from that 3 uses of the same formula. And I can do that. I think you get the picture now with the D and the P. We had a D binom and P binom. We had a D hyper and P hyper. And now we have a P Poisson, D Poisson. Right? D for density, P for probability, meaning the distribution function. It's pretty unlikely to get more than 2 on a day. That's the other way to put it, right? 0, 1, or 2 is by far the most likely scenario for a day like this. And with this in place, we could do all the probabilities, right? So let's not dwell too long on that. We could get the exact probability of seeing exactly 2 patients on a day. The expected rate was 0.3. Do you think there's a high probability of seeing exactly 2? I wouldn't expect that. That's the one I put here. The D Poisson 2 with lambda. Even in R here it's called lambda, so here we have a nice harmonization between our name and the R name in this case. Only 3 out of 100 days would have 2 patients. We could also go check. We could go check probabilities for the Poisson from 0 to we're not going to make the computer tired too much. Let's just go to 10,000. No, let's go to 1,000. Look at those. What's the probability of getting 1,000 patients? Well, as much as the computer can find, it's a 0, right? Whoa. 0, 0, zeros. Well, 0. for all practical planning of number of doctors at the Danish hospitals, experts in air pollution cases, I think the 0 starts around here already. Anyway, so that's a matter of practical decision. It just shows you how the Poisson probability sort of tops and then it goes down. They're all there, but they are basically 0 from some point, right? When you add them up, they become 1. Question? You're just waving. Several people have some uncontrollable waving things, but that's fine actually. It makes me happy. You know, it's like going around and saying, "Oh, they're all waving to me." Right? That was the Poisson probability. Now, actually, one point I want to make before we finish this little part is there is some common sense to be used in dealing with Poisson settings. The thing is, what if we were asked a different question? What if we were asked a question not related to a single day, but a question related to 3 days? The single day rate was 0.3, right? Now the question is, what is the probability to get one patient within 3 days? Whoa, 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 whoa. Don't give me those questions. I only know the rate per day. Maybe if I think twice and I tell you that common sense rules. There is no trick thing going on here. What would the 3-day intensity then be? Well, the answer is given to us down here. It will be 3 times the 1-day intensity. And then we can work with another Poisson distribution, having an intensity like this, counting events per 3 days. So we can jump between the scale easily like that. That's something we can use when we play around with this. Let's not do anything more on this. Let's instead, I believe, I'm gonna Kahoot you. Getting nervous about the right answer now. Apparently I was tired at this point yesterday. Okay, we're back on track. That was the same question I asked you before. It's going to be important to us next week, this line of thinking. We have a new top guy there. We have 2 more small issues for the next 10-15 minutes. One very brief one here.